the way I am thinking of organizing this, okay, is to divide this weekly meetings into two parts. Okay. The first part will be concerned really with if you like things like how classical topology affects quantum states, quantum theory. So this will be the first several lectures. Okay. So the focus is quantum theory, okay, and I hope that I will convince you that the way you are taught, one is taught quantum mechanics in elementary courses is simply misleading, okay, and does not tell you the full richness of quantum theory. Okay. Once this is done, okay, some of you here, I think you were mentioning this, also wanted to know about this questions of solitrons and defects. Okay. So let me see, I had some notes on that also. Okay. So solitrons and defects, by that I mean that there are a number of instances both in the context of quantum theory. Okay. In many of the quantum theoretical models, solitrons occur, okay, and defects which are closely related objects which happen, for example, in condensed matter theory, they also occur. And to have an understanding of these things, one needs, this can be talked to a certain extent purely classically, and to understand this you certainly need some information on what are called homotopy groups. So he was asking, I think somebody was asking for some introduction to homotopy groups, okay, and how these get affected. So I will hope to say something about that also. Okay. So depending on the time, by the end of the semester, end of this November, December, we should be getting somewhere. Okay, so this is the plan. Okay. I had written down the books on which I have based these things are books that we have written naturally, and they will be supplemented by material from outside. In particular for defects, to study of defects, there is a, for these things, homotopy groups there are maths books, but for defects there is in particular a review article by Mermin in Reviews of Modern Physics, which is highly recommended. Okay. The virtue of that review article, which is quite long actually, is that he painfully proves many of the theorems in homotopy theory which are by no means trivial. Okay. Many rich phenomena happen in homotopy with defects, also with solitrons, and hence with solitrons and hence in quantum theory. And this is one of the physics references for learning this subject. So these are the two topics I have considered of as trying to tell you something about. Okay. So I want to start with part 1. Okay. So in elementary quantum mechanics, for example, if you take a book, a standard book on elementary quantum mechanics, what you start from is we are taught that as follows. Okay. You start from some classical theory, okay, and you start from a classical theory. By the way, first one or two things I want to make introductory remarks, and then I will try to convince you that this naturally leads to very elementary systems where this idea of fiber bundles and gauge series occur without any effort. You need them, for example, to describe particles of even such a simple system as a particle with a fixed spin. I will show you. Okay, if you want to describe a particle with fixed spin in quantum theory, you will find out that there is underlying it some highly non-trivial topological structure, and that is what I will start with. But before that, I need to tell you some introductory material, how these things come about. Okay, so we start from a classical theory and this configuration space. Q, call it Q. Okay. For example, it may be a particle moving in 3 dimensions with a say free particle moving in 3 dimensions, and Q will be R3. Okay. Then we are taught, okay, that wave functions are functions on Q. You are taught that wave functions are functions on Q, whereas we are taught that they are smooth functions on Q, okay, and even single valued functions on Q. So there are many statements you find smooth, single valued, depending on whom you are talking about. You will find all these statements in books, okay, and then from there one tries to develop quantum theory. Unfortunately, all these statements are wrong. They are correct only in the very elementary situations, but the moment one starts talking about some more complex situation, then these statements are wrong. Okay, wave functions are not functions on Q. We shall see that they are more complicated structures, and this was already understood, okay, by Dirac in 1931. We will see how it happens, clarified, okay, that, okay, let me put it now in the wave functions are not functions on Q. I mean functions mean smooth functions, and that is simply not the case. Okay, and in fact he in his 1931 paper he develops this idea, okay, and shows that in ordinary quantum theory you have the possibility of magnetic monopoles. What he does here is to develop this formulation and to show that he proves the possibility of magnetic monopoles. And he proves that Eg over 4 pi or something is n times h bar. This is a very remarkable. He shows. You can ask me any question. I will show you how this happens. In fact, in the next couple of sentences, we will see how we deviate from that original picture, okay, of wave functions being functions. But he proves this result. This is, if you look at this, is electric charge and the magnetic charge. Okay, if you look at this result, it is very remarkable, because this says that if there are one magnetic charge, okay, implies, okay, there exists one magnetic monopole anywhere in the universe, that the ratio of 2 charges is rational. Sorry? Eg over pi is 4 pi is some unit, mk is unit, I don't know about that. But this n is integer, right? This n is an integer. Sorry, I don't understand. If you take one charge, one magnetic monopole, there is one electric charge and another electric charge. So both are n1 and n2. So this will be some n1 over n2, right? Yes?
Yeah, I was asking the question that whether it will be half integer or
Here, that depends on this 4 pi unit.
Yeah.
But that is not done by me, but that is done by somebody, some engineers. I don't know, I don't care about that. Okay. I will show you that depending on the situation, there are some new effects happen, which I will mention now. Okay. You could have you could have a composite of two integral spin objects, okay, which create half integral spin in this system also. I will also tell you why that happens. Huh? But if there is one charge, one monopole somewhere sitting quietly behind the moon, and you have two charges E1 and E2, one monopole sitting here, any one monopole, okay, but then it also implies the other way around, that if you look at two monopoles with one electric charge, the ratio of the monopole charges also will be quantized. Okay? Okay. So this means that they all come in units or some fundamental unit. Okay?
So, but why do you think that this when you say that they are not smooth function on the configuration space, are you in mind thinking about the string singularity?
No, there will be no string singularity. That would be, let us say, that is passé. You don't talk about strings. That is not the thing.
But here still the functions, the wave functions are still.
They are not functions. They are. We will see what they are. They are some sections or some bundles. Okay, so with transition functions, we will see what they are. Okay, so the whole idea of thinking about them as functions is misleading and wrong. Okay, is wrong really, okay? Because they are not. It is a Hilbert space we are dealing with, no? We are not dealing with the Hilbert space. Is not form. The Hilbert space contains all kinds of extremely bad things which you cannot differentiate. You cannot do anything. Okay. Yes. For example, yeah, it is a what we are dealing with eventually is a Hilbert space of L2 functions on Q. But nobody told you that in these functions, these objects are smooth things. Okay. They are not. Technically, they are not even functions. They are equivalence classes. If you really want, so it gets really messed up. Okay. Okay. So I will come to that. All those things. Okay? So this our formation where we are taught that we deal with functions is somehow not good. Okay. It is much more complicated than that. Okay. Quantum theory is much more complicated than classical physics. Okay. Much more rich, I would say. Okay. So he already understood this. And there for in initial time there were a lot of activities around this. Okay. But they are still going on. There are many unclarified issues which I will try to bring out. There are open problems which I will tell you. Okay. Of physical relevance, not made up problems. Okay. Okay. So this is one aspect, that the classical topology which is leading to all these effects in quantum theory cause all these remarkable results which I had pointed out and which I will try to prove. But conversely, okay, the Q classically may support say solitons, defects, etc. Purely classical solutions, and you would like to see what are the quantum theories associated to these. Okay. So this will lead to new states in quantum theory. First thing they will do is to lead to new states in quantum theory, and in turn affect, okay, their wave functions, their quantum states. Okay. So the classical topology affects quantum theory in several different ways. Okay. It affects you first by see this is by pointing out that you should not think the fact that under certain conditions it is misleading to think of quantum state vectors as smooth functions, it will lead you to wrong results or limited results. And secondly, in some cases where the classical physics admits topological structures, they turn up in quantum theory in new forms with new properties. Okay? So there is this interplay between classical physics and quantum physics which reflect the topology of your underlying configuration space. This is what we would like to understand. Okay? So let me start. Okay. It is not very clear. The problem with discussing this whole business is not. It is not clear where you start. It is not a linear development. Okay.
Whatever you have said, the configuration space is classical.
The config. Yeah. Yes. The Hilbert space is square integrable functions on the configuration space. Okay. Hilbert space is that. Okay. But it is built on a configuration space. Okay. Then the way we deal with things like Hamiltonians is that so we are dealing with now here is a so the configuration space is giving you the Hilbert space. Then we have to in this Hilbert space are somewhere inside this are structures which tell you from where it came from, okay, namely the configuration space from which you came, and how is it happening, how is it affecting our calculations, and so on. We want to understand. Okay. They may be the way they turn up may be very complicated.
So this construction of the Hilbert space, as you were saying, is it related to the GNS construction that we use?
I am not using GNS. I was told by Sujit that nobody will be interested in that, so I will not do it. I will not do it. I'll tell you the problem. In another way, it's a free discussion, no? So I'll show you immediately a problem. Okay? The statement is the following: give me any two Hilbert spaces, any two, okay, infinite dimensional Hilbert spaces are isometric. I will show you right away, just to provoke you. Okay. There is no way, there is only one Hilbert space. The only invariant you can associate to a Hilbert space is its dimension. In finite dimensions, is the number is a dimension. Infinite dimensions, if you have a basis, they are all the same. Why? Because suppose I have a Hilbert space of a harmonic oscillator H1. Okay. Then you choose a harmonic oscillator basis n, 0, 1, countable basis. This is say one dimensional harmonic. Now take a 3-dimensional harmonic oscillator. Okay. It is also a countable basis. Let me call it 0 prime, 1 prime. Every Hilbert space that we deal with has a countable basis. Yes? Okay. Now I will give you a mapping from here to here which preserves scalar products. You map n to n prime. You define an operator here u n is equal to n prime. Then you preserve scalar products. U is unitary, right? So if you give me any operator here, we will go into what? I want to write a corresponding operator here, so I will write uk u inverse u dagger acting on n prime. This is an operator, takes u dagger takes you back to n, k acts here, then I go back. So this is an operator on the other one. So this is completely identifying all operators, all observables in this Hilbert space to that Hilbert space, no difference. Okay. That means, how do you tell harmonic oscillator from a hole in the ground? They look exactly the same in quantum theory at the level of Hilbert spaces. All observables are the same, everything is the same. Okay. It is a convenience that so if this is the case, the question we want to understand, which I have some feeling for that, is then where on earth is the information about the underlying configuration space built into quantum theory? Okay. Where on earth is it? Okay. If you just give me quantum theory, I cannot tell what I am dealing with. Okay. Yes? Do you agree with the statements? Any two infinite dimensional Hilbert spaces are isomorphic. They are the same. I mean, there is only one. I mean, it's not the same. There is only one which you can write in different ways. Just like there is only one finite dimensional Hilbert space for a given dimension. So the question arises. This is a question which this is the question of the quantum baby. If you have heard about the quantum baby, given that all of us are quantum, and imagine a quantum baby brought up on a nice diet of self-adjoint operators on a Hilbert space with good vitamins and so on, and it grows up. How does it tell a hole in the ground from harmonic oscillator? How does it, because it will see everything, where is this information to it coming from? What is epistemology whereby people recognize that we are living the classical picture? How do we recognize? I think this answer to this question is not known. I think this is the fundamental question in quantum theory. But somehow when we do quantum theory, we build this information in some structures, but this is put in. Okay, it's like just like when I do hydrogen atom, I put in wave functions which are functions on R3. Okay, I could have done hydrogen atom by using harmonic oscillator one dimension wave functions. It will be very painful, but you can do it. Okay, you don't do it because so this is the problem. Okay.
Yeah, so where does the underlying classical configuration come in on this?
I don't know. A priori I do not know, because it depends upon the reconstruction of classicals. So quantum theory in this abstract form of observables which are self-adjoint, say even bounded self-adjoint operators on an infinite dimensional Hilbert space, will not tell you whatsoever that there is a classical spacetime. This is why I say that when one goes into the deep quantum regime, for example black hole physics, I think it is starting from with this visualization and then getting answers is highly misleading, can be highly misleading, because that is not how it works. I don't know the answers to this particular question, I don't know. Okay, but if you want, you can. Long ago I wrote, put a paper in the net called Bringing Up a Quantum Baby. It's good if there are mothers here. Okay, one has to be very careful. No? Highly sanitized self-adjoint operators should be fed to the baby, right? Okay. It comes, but it will deviate maybe later. There is no way to properly discuss this without looking at some operator theory, because the stuff for quantum theory is operator theory and states and so on. Okay, that is how it is made. If you like it or not, that is how it is. Okay? So we had to start from there. Okay? Then try to reconstruct our visual pictures. Can we do it? It is not known that I know. I ask people who understand these things much better than I, but they also said no. So now I will this is some by way of provocation. So now I want to see how gauge theories arise in quantum theory. These are all by way of introduction. So I will, after having done this preliminary stuff, I'll give you a short course on theory of constraints. Okay, short course means I'll just outline Dirac's theory of constraints. Okay, and then because I needed to discuss things like particles with fixed spin, magnetic monopoles, instantons, for all these things this what Dirac did appears again and again, okay, in some way, okay. So I will do that, okay. I will give you a short thing, it will by no means be exhaustive, but it will be useful. So how do we, so what we have to, what we say is the following, okay. In quantum theory, for sure wave functions psi are not observable. Right. What we can see at best are probability densities, okay. So but says psi star psi is the probability density of phi star chi, such objects may be accessible to observations. But we notice now, but this is invariant, thus does not see the phase of psi. Okay, that is psi star psi is invariant under phase change. Okay. Now very often we can take into account, we can account for this phase, okay, by one way to account for this phase is to enlarge, is to consider, is to think of wave functions psi, okay, as functions. Again I will not say anything about smoothness on, let me call it q hat, which is q cross some circle. Let me write the circle as S1. So at each point of the configuration space I am going to introduce topological notions now. So what I am doing is to take my underlying configuration space Q, then at each point I attach a circle, and I will say that my wave function, this is to take care of the phase here, I will say that psi is a mapping of q hat to say complex numbers, but it is necessary that when I, so this is a function psi takes a point here q at an exponential I theta, and this gives you a complex number, but it cannot be any arbitrary complex number, because when I take psi star psi I should not be able to see the phase, okay. So such that psi q, and I will write here exponential I alpha exponential I theta is psi of q exponential I theta exponential I alpha, okay. I will consider only such functions. So what I want to say is, so there is a u1 action, namely let me exponential I alpha taking q exponential I theta to q exponential I alpha exponential I theta, I impose this condition. This is an imposition. I will only consider such functions. Okay, this is sort of trivial. Why? Because I can such things, if it happens, and my configuration space is like this, I can always write this as psi q1 times a phase, right? So it's not a trivial. I'll go immediately to non-trivial cases now. This I can always do. Okay, this looks stupid, but we will deviate from stupidity in a minute. Okay, if I have this. So there is a U1 action. U1 is I want you to distinguish this S1 from this U1 such that psi q psi fulfills this property. Okay. This one. Okay. This will imply that psi star psi. It is invariant by this, the phase cancels out. So this thing is a function on Q. Okay. So the probability interpretation is possible because this phase cancels out. Okay. Sorry? Add. They all have the same property here. So this is a very good question. You must have the same so all size must fulfill 1. So all of them will change by the same phase. Then if you add it, they will also change by the same phase. So even if under addition, this property will be fulfilled. Okay, this is an example for you of a super selection rule. Because if you take one wave function transforming like this, and another one with 2i alpha there, and you try adding them, then the probability density will depend on this alpha, and you will get nonsense. Okay, so this is already an example of a super selection rule. Okay, now. So you must put the same thing here. You can choose a fixed weight, maybe m alpha you can choose, where m is some integer, but it must be the same weight for all wave functions which you superpose. Okay, this already shows you that when you are taught that there is a superposition principle, it cannot be exactly correct because certain wave functions cannot be superposed. For example, one transforming with an exponential I alpha here, and another transforming with exponential 2i alpha here cannot be superposed. If you superpose it and you look at the probability density, it will not be a function on your configuration space. Right?
I have a question. The phase corresponding to I alpha is getting cancelled out. But what about the theta? The phase
So I just choose alpha equal to minus theta,
Oh, I see.
then it cancels out. But this is sort of easy.
But when alpha is not equal to theta, then
No, it won't be there because whatever it is I am looking at this object psi star psi. So I simply, this implies in this case, this implies that psi of q exponential I theta is some psi of q1 in this particular case exponential I theta, right, and it cancels out in this particular case. This is by way of introduction how these phases play a role. But the interesting aspect which Dirac understood was, but basically Dirac does it, and it's also done by Hopf in mathematics. There are a variety of cases where there are cases where input circles S1 on Q. On my at each point I put a circle such that eventually at each point I have a circle, eventually what I get, q bar is not this Cartesian product. So I put this, I will show you an example, but I put these circles, at some point I twist things in some particular way so that this decomposition does not happen, okay. But still, this is the important point, still, okay, q hat has a u1 action, okay. So q hat going to some q hat exponential I alpha. So it is, this is taking you along this circle locally. At each point I have an S1, so this is this q, and at each point I have an S1, and this exponential I alpha is taking you around this, okay, at each point. But the whole thing doesn't look like this. So if this is happening, okay, then so we can look at, welcome, we can consider wave functions. I'll come in a minute. Psi on q hat such that psi q hat exponential I alpha is psi of q hat exponential I alpha, implying psi star psi is a function on a q. Okay, what is the question?
Question is, if you have a circle at each point on q,
Hmm.
then why wouldn't you look like q process 1?
I'll show you. I'll give an example.
Self-intersecting case?
Huh?
Does that have to do with the case when it is self-intersecting?
It won't. There won't be anything. Everything will be smooth, but it will be some twist, something. Okay, it's like braids or some funny thing you have done. You know?
You are essentially saying that we can see this as a product space
Locally, not globally. Locally, look like we have put circles. Okay, so and I will be able to construct. So locally, there is still a u1 action. It takes you along this fiber.
left action. You are particularly choosing the left one there. When you are talking about the even action over there,
Yeah.
choosing a particularly left action.
But I was careless here. But normally there is only one action. Okay, so I write it on the right. Okay? It doesn't matter. Okay, it's not a group. The larger thing is some manifold. I'll write it for it what it is. I'll give you an example. So we are not. Okay, but since if I look at only wave functions like this, which under this action changes by a phase, and I'll show you that they exist, then psi star psi, this, because of this invariance under this one phase, one degree of freedom is lost. Okay, so you would expect that this is a function on q. One can prove it. Okay, then so probability interpretation is still possible, but you can no longer fix the phase. Okay, so okay, quantum mechanics probability interpretation is possible. Possible, okay, but we cannot smoothly get rid of the phase. Okay, by writing, okay, by what? By trying to write, writing say q hat as some q cross some phase, some exponential I theta, and fixing theta. This is not possible. Here in the previous case I could write q hat as like this, no? Then I can choose theta some value. Okay, so this degree of freedom will be lost, and will be the function I am dealing here in this case will be really, this is a redundancy. I could as well deal with q, but now I cannot do it because that object is not living, this wave function is not living on q cross S1, okay. It is living on some other space, okay. So if you try fixing this phase locally, you can do it in some small region, you can write like this, and suppose you try fixing this theta, you will find that you will get into singularities as you keep going, okay. So if you try doing that, then you will be ending with wave function, well, vector space which are no longer smooth functions, giving you an illustration of my previous remarks that wave functions are not really functions, okay. So let me give you an example. This example will come again, this is the example, okay. So what I do is, for this example is the following. Let us consider S3, okay. So this I will coordinate S3, the 3-dimensional sphere, okay. So I will choose coordinates of S3 as 2 complex variables, and I will put the condition modulus of zi squared equal to 1. So there are 4 real variables with 1 constraint, so I get a 3-dimensional sphere. Now on this 3-dimensional sphere, U1 is a unitary group, okay, of is phase acts by this zi going to some exponential I alpha zi. Yes, this maintains that condition, okay. So now okay, we want wave functions, okay. So functions invariant by this action are, let us write z dagger z and z dagger tau I z, let me call this Ni, but tau I are Pauli matrices, there are 4 of them here, right. This does not change by the phase, there are 3 of them, this does not change, but this is 1, so this is not interesting. So there are 3 Ni, but a short calculation shows you, check, n dot n is 1. Okay, it's a very trivial calculation to write it down. Use this relationship I got here, and you find that this n is normalized to 1. And we also see by inspection that n is real, n bar is n, because of the fact that Pauli matrices are Hermitian. So what is this? You know what this is? There are 3 real vectors normalized to 1. So the n's here span a 2-dimensional sphere. Huh? It's a Hopf vibration, right? So what happens is, so wave functions size are functions on S3, okay, and I will put the condition that psi, if I multiply by a phase, it changes by a phase. I will give you examples, explicit example which you may know. Okay, I will find these functions, and if I do this, then psi star psi, if I take these functions, function on S2, this example will occupy us, will come again and again. The simplest example of something non-trivial. So I can do quantum mechanics on the two-dimensional sphere perfectly well, but all we are taught in ordinary quantum mechanics is wrong, because you cannot write wave functions in this case. Okay, you can contemplate wave functions which are not smooth functions on your configuration space. Okay, they are much more complicated. So can I show an example of this? Okay, so let me show an example of one. In fact, I will show you many examples. It is sort of, well, I will give you an example in terms which some of you may be familiar with, but it is obvious that because of the fact that I am transforming z's like this, okay, any homogeneous function of a fixed degree in z, okay. So simplest way is choose, okay, k fixed and let us say positive, and let psi be a function of zi z bar I, okay, with homogeneity k. That means is a function of what? Some any multi-index, okay, n1 z j and j, right, and then some complex conjugates, alpha 1 say alpha j plus k.
So does that mean?
Let me write ij homogeneity k, let me equal to k.
So when you say that psi is not a smooth function, does that mean when you take the Schrodinger equation and you have derivatives in the Schrodinger, so those are not exact?
Yes, there is problem.
So
There are
what are the
problems.
solutions of the Schrodinger equation that we use in quantum mechanics?
That kind of equation that you are telling won't work here. That kind of equation for the Laplacian won't work here. The Laplacian will be some Laplacian on with a which I will show you what they are. Okay. So the standard way of writing Schrodinger equation also will not work. Okay. Everything that you learnt will there is a novel by Chinua Achebe, if you know him, okay, called Things Fall Apart. Okay. He is talking about Ghana, okay, and social changes there. Like this here, everything will fall apart. Okay. So what? But there is another way of writing this. Okay. So this, if I do this, take anything like this. So this is a fixed homogeneity degree. You can choose. So the phases will cancel and k will be left over. So what will happen is that this alpha will become k alpha, but fixed k. You cannot choose two different k's.
What is k?
K is anything you fix. You will get different quantum theory for each choice of k. There are lot of possibilities for each k integer positive you choose, you will get an answer. I can also choose k negative by increasing things here. So what are these things? I will come back to this later. Well, another way of looking at this is the following, and this is very useful. Okay. Another way. Okay. Let G be in SU2. So I like 2 by 2 matrices. So then I can write G, a canonical way of writing it is Z1 Z2 minus Z2 bar Z1 bar. Notice that this is unitary and determinant of G is 1. Okay. So every pair of complex variables I can write this G. Okay. This is another way of writing this function on two complex variables. With the, huh? This is S3. This is a statement So S3, this is topologically an S3. Now see what happens if I multiply this by exponential I sigma 3 alpha on the right. So equal to Z, it disappears in quantum theory. The reason is just this, that the wave functions are not functions of your configuration space. They are living somewhere else. Their relation to configuration space is somewhat distant. In this simple case you see it rather clearly. But in more complicated cases it gets more and more hairy. So this you see examples. You see parity breaking in a simple way. But in quantum theory there are very many classic examples. So anomalies. Okay. Parity. Let me just list it. For charge monopole system. Then you have axial anomaly in QCD and many other things. But all of these things happen because of this. Now, as a last remark, I'll say, note. We can replace U1 by any, let's say, compact group. That is, instead of imagining that just a U1 group is acting, you might have some compact group. For example, it could be discrete. Okay. So discrete groups happen in molecule physics. We will again show you. Here, some of you may not know group theory. Never mind, I'll come back. Okay. Continuous, more complicated, higher rank groups. Okay. There are plenty of examples. Molecular physics is full of these examples. Unfortunately, people do molecular physics are not conscious of this defect. Okay. Which I think is regrettable. Okay. Because otherwise they would have found out this result about spin half from spin integral spin long ago. It happens in molecular physics quite routinely. There could also be some more higher rank group. For example, it could be SU2, continuous. An example is SU2. That is, instead of U1 here, you get SU, put SU2. Whereas this happens, for example, in instantons. And so on. There are many examples, and we will see how this is. And in gravity is certainly most exciting thing to know, because there are things which we don't even understand. For example, in gravity, these groups which come into gravity are very complicated, and furthermore, because in gravity, people say that there should be diffeomorphism invariance. And even Poincare group is part of this diffeomorphism group. Not only are there technical problems, but there are also very deep conceptual problems, which I think are not understood. Okay? So there are all these things. So in the next class, okay, what I will do is I will try to tell you how this extra U1 phase is reflected in a class in a Lagrangian formulation. It's quite generic if you have a U1 case. And you will see immediately that if you try to incorporate this extra U1 in a twisted case using a Lagrangian, you will necessarily get a gauge group, okay, which is highly not trivial in its action on the Lagrangian. Okay. Then quantization of the Lagrangian, you cannot fix a gauge. Okay. So it is not true that you can fix gauge all the time. For a particular fixed spin, you cannot do it. Okay. So how do you quantize it? And there I will, for that purpose, I will outline for you as a beginning Dirac's theory of constraints, not in all its complexity, but enough so that we can handle it. Then I will show you how to deal with particles of fixed spin. So I am taking the most trivial examples I can imagine. Then I will do magnetic charge monopole system. Then from there I will try to make situation more and more complicated, maybe deal with the QCD theta angle from that point of view, and then maybe deal a little bit with gravity. And by that time I think we would have run out of time, so I will try to shift to solitons and monopoles. That's it. If you have questions, you can ask.
So what you said about the Laplacian will be the square of the angular momentum.
Yes.
So can the derivatives in the Laplacian operator can be the fractional order in that case? In such a case?
They won't be fractional because the square of the angular momentum is acting on these three functions. It will give you j into j plus 1.